check this guy is actually lining above this vertex right here. So this is the plane cutting through the hyperboloid with one branch of the shape. So this is going to be the solid region. Okay, so it is bounded below by this hyperboloid and above by the plane. Okay. I can quickly check this plane does lie above the vertex because you can identify this vertex as 0, 0, and 4, all right? This is definitely 4 right here. And 2 square root of 5 is greater than 4, right? It's 2 square root of 5, I have 2 times 2. Square root of 5 is greater than 2, so this one is a great quantity. So that's why I have the plane to lie above the vertex right here. So I'm bounding these two. So I want to find this volume. I want to find this volume. And we already talked about the application of two-point integral. If I want to find the volume of a solid, let's call it as a D. I only need to take the three-point integral of D with respect to the integrating function 1. All right? This is going to be the volume. Okay? And then I need to evaluate a three-point integral in the cylindrical coordinate system because I have x squared plus y squared. Right? So I need to identify this, where I can easily identify Z is going to be bounded between the hyperboloid and the plane. Right? So it's going to go from square root of 16 minus x squared plus y squared to 2 square root of 5. And then I need to identify the region R as a polar region. And this R is exactly the projection of this solid back onto the xy plane. All right? It's the projection back on the xy plane. Or, if you will, it's really this disk as the intersecting between the interior of the hyperboloid with the plane. All right? It's really this disk. I need to find the intersection between these two surfaces. All right? How do I find the intersection?
So
Make them equal to each other. This is pretty easy. So it's 16 plus x squared plus y squared is equal to 2 square root of 5. I square both sides and do all the mathematics. It's going to be 20, so it's going to be 4. Okay? So this R as the projection is nothing but a radius 2 disk. All right? It's a radius 2 disk. So if I do that, this is going to be from 0 to 2 pi, from 0 to 2. Then from square root of 16 plus r squared to 2 square root of 5, then 1 dz dr dz. Okay? Oh, I have one more factor r coming. So this is going to be the volume of the solid. Okay. So the key part is to identify as an integral and then write it in one of the representations. Okay, the following remark I want to make. If you don't understand it, forget about it. Okay? But I do want to link back to double integral. And I want to help you understand the simplicity of the cylindrical coordinate system. So if you want to evaluate the volume of this solid, not using triple integral, but using double integral, what will you do? If you're doing that, what will you do?
Would you subtract the 2z?
You're simply still taking the double integral with respect to the same region R here. So this is going to be the region R as the projection. You're still taking the double integral of R and also the difference between the upper function and lower function. The upper function is 2 square root of 5. The lower function is square root of 16 minus plus x squared plus y squared. And the area. All right? You're still doing a double integral as the difference between the two functions. And if I want to identify this as a polar region, which I'm going to do that because I have x squared plus y squared. So this is going to be from 0 to 2 pi, from 0 to 2 square root of 5 minus square root of 16 plus r squared, and then I need to multiply by r dr d theta. If you compare these two, they are exactly doing the same thing, in fact, right? Because if I'm eliminate the z variable, I'm getting 2 square root of 5 minus square root of 16 plus r squared multiplied by r again. All right? So in fact, this triple integral is nothing but a double integral over there. And this is no coincidence, because we agreed on this in the very beginning. A cylindrical coordinate system is nothing but a polar plus a variable, right? Even though we name it in a fancy term, it's a cylindrical coordinate system, but really you're doing a polar double integral. That's it. Okay? So you can evaluate this volume by using triple integral, or you can even go back to the double integral to the old trick. Okay? Questions? If not, we're gonna move forward to the very last system we're gonna discuss, which is a spherical coordinate system. So a cylindrical coordinate system is only a polar plus a z variable. It is simple, and sometimes you don't even realize you're using it. But I have to warn you, spherical coordinate system is totally different. Okay? Okay. So the spherical coordinate system uses 3 variables as well. So rho, phi, and theta. Usually, we want to go back to the rectangular system, which is x, y, and z, and connect these two. Okay. I didn't even give the formula to connect between cylindrical coordinate system and the rectangular coordinate system. For again the same reason. That connection, that relation is exactly the same as the polar with rectangle, because z is still z, x, y, and r theta are connected as usual. Right? So that formula is the same as we discussed in 2-dimensional case. But for our spherical coordinate system, it's going to be different. Am I writing this wrong? I have an E right here, right? Right here. Spherical coordinate system. Okay, so I want to have the picture right here. So in a space, when you have 3 degrees of freedom, no matter which system you're using, you definitely need 3 variables, right? The only thing is you need to give the meanings of the 3 variables, what they mean. For x and y and z, you have the rectangular meaning, what the distance between planes, and that's the one. But for a spherical coordinate system, you probably already know what rho means. Rho is the radius, right? Rho is the radius, or the distance. Basically, a coordinate system is, if I have a point, I want a triple of numbers to uniquely determine where it is. All right? If you ask yourself, what do we mean by a coordinate system? That's basically what it means. If I have a point in a space, how am I going to locate this point uniquely by 3 numbers? You can use x, y, z. I can also use rho, phi, and theta. Rho is the distance between the origin and this point. And phi is the angle between this ray and a positive direction of the z-axis. So this is the angle phi. Okay? So this is the angle phi. And then theta is going to be the angle if I project this ray back onto the xy plane, the angle between the projection and the positive direction of x-axis. Okay? So this distance is called rho. This angle is phi, and this angle is theta. Okay? So once I heard this very interesting remark, one of the primary goals for calculus is to learn Greek alphabet. So you learn about the alpha, beta, this theta. I usually call this phi. Some people call it phi. I prefer to call it phi, and this is rho. Okay? You pretty much pick a lot of the Greek alphabet. Okay? So now, if I have these relations, I can translate this back and forth. Are you with me? Rho is the distance, and phi is the angle between the positive direction of the z-axis and the ray, and I can project this ray back onto the xy plane, and I have the angle between the projection and positive direction of x-axis. So this is the angle theta. And these angles are designed in a very useful way, you will see in a minute. But I want to quickly write down the relation between these three variables with x and y and z. So first one, rho squared is equal to x squared plus y squared plus z squared. So rho is equal to x squared plus y squared plus z squared. This is probably the easiest. Am I right? This is probably the easiest. Okay. And the other relation between these two are all connected by trigonometry, right? If you have an angle, definitely you have to use trigonometry. Am I right? So angle and trigonometry are born hand by hand. So they are, if you have an angle, basically you want to use trigonometry. So if I have this angle phi, if I draw a vertical line passing through this point and intersect perpendicularly with the axis, so if this is a right angle, I can immediately connect rho, z, and the angle phi. All right? Yes? So in this right angle, z is going to be equal to rho multiplied by cosine phi. So z is equal to rho times cosine phi. I'm not writing them in the x, y, z order, but I want to write it in a logical order. Okay? Logically, I can draw a line here, so I can quickly find the relation between z and rho here. So I can find z is equal to rho multiplied by cosine phi, or cosine phi is equal to z divided by rho. All right? So I want to have 6 equations in total. Right? 3 equations there, 3 equations here. So rho is equal to cosine phi. The angle theta and a relation between theta and xy is still the old one. All right? If you look at this projection back on the xy plane, it is still a polar relation, which means tan theta is equal to y divided by x as usual. So if you draw a vertical line or perpendicularly with x-axis, so if this is a vertical line with x-axis, so this is the angle theta, this is y, this is x. So tan theta is going to be equal to y divided by x. Okay? So the relation between rho and xy is indirect, but they are related to the projection. Right? So this projection has the same length as this side. And this side has the length rho times sine phi. Right? So which means this guy is equal to rho sine phi. So if I know this side has a rho sine phi as its length within this right angle, I can quickly write down what x is and what y is. All right? So this side is rho times sine phi, and this is angle theta. So x is going to be equal to rho sine phi multiplied by cosine theta. All right? So in this right angle, okay? This is a right angle here. This is the right angle with this side equals rho sine phi. So x is going to be cosine theta. Y is going to be rho sine phi sine theta. So these are the relations between the spherical coordinate system and a rectangular coordinate system. Okay? Questions? Okay, so this is the formula, but I want you to have a geometric understanding about what this spherical coordinates actually mean. So you can actually play around with these coordinates a lot, okay, and understand what they mean. So here is what I want to understand in the following. I give you 2 ways to understand spherical coordinate system. You can derive the formula afterwards. But this is the idea you want to keep in mind. I want to see what the function means if I fix rho as a constant. Okay? if I have the distance between the points with the origin as a constant distance, what does it mean for this function, this equation? It's going to be a sphere with radius rho, am I right? So it's going to be a sphere with radius rho. Or you can simply understand this question in the following. If I ask you, if I group all the points together, these points all have the same distance rho with the origin, what will the family be? Right? It's definitely a sphere. And actually the definition of sphere is exactly the collection of points which have the same distance as the radius with the origin. Alright? That's the definition of a sphere. I want you to also understand what it means for phi is equal to constant. If my phi is equal to constant, then that means the angle between the ray with the positive direction of the z-axis is a fixed angle, right? So if you can imagine, I'm fixing this origin, and then I have a ray pointing from the origin, and this ray can change, but the angle between this ray and positive direction of z-axis cannot change as the angle.
So it's a cone.
So you can rotate it around the z-axis, am I right? Can you imagine that? If the angle is fixed, then you can rotate this ray around z-axis with the angle still fixed as phi. So basically, you're going to get a half of a cone, am I right? You're going to get a half of a cone, and this angle is exactly given by phi. Okay? So the radius can change, which means along each ray, you can go near the origin, you can go further from the origin. All right? Theta can change, and that is essentially giving you the rotation around the axis. Can you understand what I'm saying here? So theta here is exactly talking about how I can rotate this ray with respect to the z-axis. All right? So if I rotate a whole circle, then the theta will go from 0 to 2 pi. Am I right? 0 from 2 pi. So I can rotate around the z-axis for a whole circle. If I change from rho equals 0 to rho equals infinity, I'm going to get the whole ray on one direction. All right? So that's the direction, and that's the distance, and this is the rotation. So basically, if I want to see what the theta is equal to constant means, so if theta is equal to constant,